Hey, my name is Zeke Mostov. I'm one of the founding engineers at Turnkey, and I'm going to talk today about Turnkey Verifiable Cloud. So I'm going to give a quick whirlwind tour, and then we'll try to spend the second half of this talking about our new private verifiable file system primitive. I'm going to present on who is building TVC, what is Turnkey doing today, why did Turnkey choose to build on enclaves originally, why do we decide to build Turnkey Verifiable Cloud and externalize that enclave stack, what are the layers of this stack, how did we build a persistent file system primitive, and finally, what does this unlock for building private AI systems? Going to cover a lot, so I might move some of the first parts quickly, and then I'll try and later on stop for potentially clarifying questions. Our team has a unique intersection of experience, from early on. Originally, we set out to build a best-in-class key management system about 4 years ago. The founding team scaled Coinbase custody from 0 to hundreds of billions of dollars of assets under management. Because we are in this blockchain space, we haven't had this rare mix of expertise of years working with highly optimized Merkle tree systems and research level experience of classic Web 2 databases. And we also just happen to have several engineers with experience working on Linux kernels and VMs. So today, Turnkey, the key management system, is actively securing hundreds of billions of dollars of assets. Daily, we move hundreds of millions of dollars just of stable coins, and that's the stuff we can measure. And crypto operations like signing take sub 100 milliseconds at our system's edge. When we started to build Turnkey, we needed a way to securely process policies and use private keys at scale. With the deep Linux and VM expertise we had, and years of experience doing billion-dollar-plus transactions, but in more of a kind of cold fashion, we knew enclaves were the best bet. And this was kind of counter to MPC, which was back in 2022, was kind of the big thing at the time. However, these enclave platforms, you couldn't just go and be like, oh, I'm going to deploy my code in enclave and we're all good. We basically spent the first 2 years at Turnkey building out a custom operating system, special air-gap tooling, and a lot of custom Kubernetes components and parts of the operating system to deal with horizontally scaling and code upgrades. So after we got Turnkey to market, we had existing customers just start asking us to use enclaves. They were attempting to run enclaves themselves. Sometimes they're using our custom operating system, CormOS, which is fully open source, and I'll talk about in a bit, but they were struggling. These customers were asking if there was literally any amount of money they could pay us to run enclaves. And after you get a few enough requests like that, you're like, okay, we should probably put some people on this. It's already K8s under the hood, so you're just hitting some APIs and making K8s resources, so it's like, let's do it. I'll cover the components of the stack in more depth, but at a really high level, we got deterministic builds, right? You need to verify every single byte of code, every line of code that's running in the enclaves, and we want customers, every end user, to be able to verify that. We have a custom operating system. We have the enclaves themselves, and then we have all the stuff to productionize that. So more details. The major layers of the stack, CormOS, the operating system. We had someone for almost a year building StageX deterministic build tooling, and that is now a pretty sizable open source ecosystem that's maintaining itself. We have control plane infrastructure to deal with the enclaves and the key forwarding to horizontally scale. And for the type of clients we deal with, we're ultra high uptime. They cannot take a second of their signing infrastructure being down. We built out what I'll explain later, but we're calling them boot proofs and app proofs. As first-class citizens, so we can verify every action the enclaves take. And we have key management company, so the app proofs from these authorize directly into our system and are built into our policy engine. So you can write policies against your app proofs that your enclave is producing. And kind of the big thing that I'm going to talk about at the end here is this verifiable confidential state with rollback protection. Okay, diving in, StageX. So kind of, I think Marvin hinted at it earlier, but like, what's the point of running stuff in an enclave if you can't, and getting these attestations if you can't verify byte for byte everything you built? So we didn't just say, hey, we want to build Rust deterministically, or we want to build Go deterministically. We said we wanted to build the toolchain from scratch, have the toolchain build itself and bootstrap itself deterministically. That starts with 190 bytes of assembly, goes through all the libc toolchains, and then you start building Rust toolchain or Go toolchain. And now it's an open source ecosystem. We kind of are reaping the benefits of getting other languages, like people are packaging up whole node Python runtimes. But kind of it's like what you can do with this, and this is all Docker based. So your build is in a Docker image, it's portable, you can do it anywhere. On my machine, before we deploy code, I'm one of many people at our company who will hit reproduce on the build before we have a quorum of operators sign over the binary hashes. So this is critical. We have a custom OS engineered for verifiability. There's a bunch of parts of Quorum OS. I'm not going to get into all of it, but high level, ultra minimal, ultra hardened kernel. All provisioning operations are designed into the operating system with Quorum cooperation in mind. Our threat model means that we do not tolerate a single developer compromise. And it's designed from the ground up to prove every aspect of what's running, from the kernel to the application binary to the runtime configuration to the deployment and approval groups. And we've been running it for over 3 years in production and securing hundreds of billions of dollars on it every day. So as part of Quorum OS, one part I want to zoom in on was what we call the quorum key and the ephemeral key. The quorum key is persistent across application deployments and survives application upgrades. So it's primarily useful for encrypting long-lived data. We'll see later why that's super helpful and kind of one of the main challenges. And the ephemeral key gets generated at enclave boot, and it never leaves the enclave. So signatures from the ephemeral key basically tie us back cryptographically to an exact enclave instance. These get the public key of the ephemeral key through Quorum OS gets embedded in the attestation documents that we get from the hardware. So we get proofs as first-class citizens. And this was critical for us if we were going to be rolling out enclaves. And kind of for the initial set of customers that we kind of onboarded, this is what ties everything together. So every time an enclave boots, our infrastructure stores what we call the boot proof. The boot proof contains an attestation from the hardware. All the details of this deployment described in the Quorum OS manifest roll up into this hardware attestation. This gives us a cryptographic trust anchor for exactly what's running in the enclave, and we also prove the enclave data center integrity. Included in the attestation document is the ephemeral key. So basically what we're doing is we're verifying the attestation document is saying, hey, this is the exact measurements of the Linux kernel that's running. From that, we know Quorum OS is running. Quorum OS is what makes the actual call to the hardware attestation and embeds the Quorum OS manifest and the ephemeral key. So we know, based on this initial bootstrapping of trust, we can extrapolate and then have more application-specific verification. The enclave exposes a simple API for the applications to use ephemeral keys, and we store boot proofs, and we already have a public API for boot proofs that you can use for our existing enclaves that we're doing for our key management system. So a benefit as proofs as the first-class primitives is we can effectively use them as a form of authorization. In other words, code can authenticate directly to approve your turnkey signing request. In the Turnkey policy engine, we have support for verifying boot proofs, writing policies against the Quorum OS manifests, and verifying the ephemeral key signature against all of this. So together, we can do things like have LLMs authorizing directly to turnkey signatures without worrying about them having access to keys, without worrying about humans in the loop. And we have consensus built in as a first-class primitive to our policy engine. So if you do want other machines in the loop or humans in the loop, you can leverage our consensus system, and we will store basically the approvals over these requests. OK, so the part I'm excited to talk about, kind of something we've been cooking up recently because it's been very in high demand by all these customers that are asking us, is verifiable persistent state that is fully confidential and mutable from enclaves and rollback resistant. So you're like, well, why is persistent state so hard? It sounds like you have an operating system in there, and it's a Linux operating system, and it has a file system. Well, the enclave secure boundary only includes in-memory file system. This means that while they have a file system, between boots, everything gets wiped. And if you're familiar with operating at a cloud scale, it's cattle, not pets. Enclaves can go down anytime. So this is totally, I'm not going to like stream in my database and then cross my fingers and hope it doesn't go down. That's not how you run code. So we were just like, what if we could just somehow make this persistent? File system is the foundation for every other type of database you're probably going to want. So it's the perfect level of abstraction to target. So we were kind of like, well, how do we make it verifiable, confidential, rollback resistant, and importantly, invisible to the app, so people can actually develop applications without sinking months into figuring out how to get this state right. So here's the fundamental architecture. Gonna try and, slow down a little bit to walk through this. Basically what we have is untrusted, you can imagine like a volume mount outside of the enclave. This is fully encrypted. This is something that's like already happens a lot. You'll see with something called Luke's, I think I'm pronouncing it right. You do file system encryption. And then there's another part here is that I'm abstracting over a bit, but it's a root store of Merkle trees. This is where you get the rollback protection, because you need to make sure those Merkle roots are recent. In a blockchain, you know the most recent block, and that has the most recent Merkle root, so you know where your state to pick up from. So what we do is inside of the enclave, we run a user space daemon that deals with decrypting. It deals with verifying the Merkle root as it's reading in data. And what it exposes to the enclave application is this fully verified file system.
So how do you know I have the latest?
How do you know what?
The latest root store, because that could be old as well.
Yes, exactly. So let me show the other path, and then I'll dive into that. So write's going the other direction. You're writing to the file system. This inevitably is updating the file system and updating Merkle roots, and those need to be published. Something we have at Turnkey today since we launched, we needed rollback protected data. We needed fully verifiable data. All of our customers' policies and kind of the really important resources need to live up to this. So you can't add an API key, and then later on you're like, oh, that API key is old, or like an attacker has access to it. I need to revoke it, right? So I need rollback protection. So right now in our proof of concepts, we're actually publishing these Merkle roots to our Merkle tree that all of our data rolls up into. We are kind of, I think, working with the first few customers of like, where is the ideal place for them to publish, right? We could do a blockchain, but for a lot of applications, that's way too slow and comes with issues of verifying that themselves. Kind of the current thinking, and what will probably work for a lot of customers, is most people will probably use a Merkle tree that we will maintain ourselves. And that itself can be a single instance enclave. Or we've talked about literally building an ultra low latency blockchain that we're just running internally, and that people can then verify themselves with light clients or running their own client. This is an open design space question. I will also say, like, the actual Merkle tree we use, like, we have implementations, proof of concepts with like our own Merkle trees we've used. We've had commonware Merkle trees. We're using ZFS, which is a very popular file system. So a lot of these details are still being figured out as we productionize it. But does that answer your question?
Let's take off.
I mean, like.
No, I guess.
Yeah.
Again, either you talk to like many routes, if you just talk to one or three, and then.
Yeah. Oh, okay. Yeah. So we have trusted timestamps. So we can say that. We could say, like, let's say there's this Merkle root rolls up to another Merkle tree. If we are stamping, if we know that tree it rolls up into is like, we say, okay, this timestamp has to be in the last 500 milliseconds, then we can verify the window.
Your TV also has to have like trusted time.
Yes.
You might not do.
Yes. So we make some trust assumptions in the system with the time synchronization primitives in the TEs that we are doing the timestamping with, and the verification of the timestamps. There's like we cross-reference, what we actually do in practice is we cross-reference a few time sources, kind KVM hypervisor clock. There's also a hardware module that we can get timestamps from. And then also we have another lever to pull, which is calling out to the host and the time synchronization primitives that are like NTP that are standard provided. So what I'll say for that is coming from the Web3 space, you're used to doing stuff in really adversarial environments, and you assume the worst case. Pulling some of these timestamp levers, it's not perfect in a decentralized world, but it kind of goes back to a lot of the trust models that we do run with the hypervisors working, with the hardware that is controlling I/O working in the data center, and some of these integrity guarantees. So the way we kind of deal with it internally and explain it to customers is they can choose not to use this, right, if that doesn't work for them. But everything's fully verifiable. You can opt into what guarantees you're choosing. And this works for the people who end up using us, basically. But it doesn't work for everyone. Yes.
Couple of questions. So one is, why are there any like obvious outstanding security risks here?
Yeah.
I'm asking at a high level only because like
yeah.
Somebody else done this before.
I don't know. I'm kind of hoping someone's going to tell me they have done it before, and I'm like, this is I don't fully like. There are security risks, but I don't know if there's any new one for this particular construction. We'll probably, as we get farther along, like figure out more attack vectors and stuff, and kind of depends on threat models and stuff. But yeah.
And then the other question is, have you explored shared state between different keys or like different orders?
Yes. So do you mean for keys in particular?
Or for anything.
Okay. So for keys, you can leverage the KMS, which is like kind of our Keyman Turnkey Classic, whatever you want to call it. You can leverage Turnkey. We have policy engine that does consensus policies, super granular control. It's like basically arbitrarily programmable. So in that sense, you can have multi-parties authorize, kind of comes into LLMs and different levels of permissioning for different actions. You might want to have other parties have to work together. I will get to in a second models where you can basically have other enclaves working together in different levels of permissioning. So actually, next thing. So we have the primitive. Let's make it really useful. Let's make it really useful. And let's just make it like Web 2 style development. So file system's cool, but there's data synchronization and permissioning, who's gonna write, indexing, looking up data, and you're like, okay, well, they solved that issue. It's, Postgres is really popular. There's a lot of other databases we can run, but we run Postgres. A lot of people run Postgres. We like it. So our plan is to have the first, we have proof of concepts for this, but we're far away from productionizing. It's hard to run, but normal Postgres, basically. So it runs inside the enclave. It runs on top of the file system, and you keep it as plain and simple and as boring as possible, because this is what everyone wants. They want, your Claude, your Codex 5.5 is going to rip writing codecs. You're going to ship your app really quickly. It's going to be performant. You can tune the shit out of it. Yeah, kind of what I was saying. The magic's all underneath the hood. Postgres has been around, I think, for 25 plus years. So just make the file system trustworthy and run Postgres. Don't reinvent it. The big thing that comes up, honestly, is okay, if Postgres is boring, kind of authentication. So I guess the way to think about this is normally when you're running Postgres, you have one writer instance, and you may have, if you have a lot of load, you might have read-only instances, and these are basically other Postgres instances which lag behind maybe 100 or a few hundred milliseconds, and those will scale up your read load, but you only have one writer. And this is how you deal with getting state consistency. So that writer is streaming out information. But then it's okay, who can write, right? That's a big thing. Kind of the way we're doing it right now is the query will be signed by the ephemeral key. You can encrypt it straight to the enclave, you can encrypt it to the ephemeral key, and then same likewise for the responses. One enclave, there's an enclave that's authorizing, it's going one way, and coming back, you're gonna have Postgres signing over its result. So is it performant? Basically, so far it is. We haven't hammered the shit out of it, but so far it's doing pretty good. It's a hell of a lot more performant than anything that we're doing right now. I could tell you it's a lot more performant than kind of the scale we're seeing with these like more blockchain, if you're just doing a straight Merkle tree blockchain database type thing. But we have some levers to pull if it becomes an issue. Still like kind of cache size and stuff and Postgres tooling and throughput between outside of the enclave and inside. Honestly, a big reason why we're doing this is we really, really, really need it ourselves. We have a bunch of customers asking for it, but even when you have a bunch of customers asking for stuff, we've seen this as kind of like, do we still want to build it? Like it's going to take some time and effort. And the thing is for us is like, we do verifiable data and private data like at scale right now. And it is honestly like probably our nastiest scaling problem. So for us right now, if we do an org data migration, it literally takes weeks. We have object-oriented storage that rolls up into this big Merkle tree, and doing all of that takes weeks. We have, I don't know how many wallets and these data structures and stuff, but it takes forever. It's a nightmare. We're always like trying to figure out ways around, trying to modify it. So for us, it's literally applying a SQL migration, which if you've done it before is instantaneous, basically. And it solves a lot of our issues with we're having to like denormalize data so our front ends can query it and customers can query it, but then get the right permissioning on it. We can just kind of all lay it out as normal SQL. You're just building a normal Web 2 app. I tried to enumerate stuff this is going to unlock. I think kind of you could imagine like there's like way more stuff than I can think of. But you could make any database query fully provable, right? Like if you've been in the Web3 space for a while, this is kind of like a silver bullet. So you can prove, similar to the blockchain, you can prove exactly what was updated. You can have permission on who can update what part. Only certain parties can authorize state. Only certain parties can touch state. And to give you guys more of a concrete mental model, it might not be like the Postgres enclave itself is doing all this, but you will have enclaves that talk to Postgres that are then serving these APIs, right? So yeah, this can be helpful in the context of attributing, reads and writes to agents. You can do privacy preserving authorization. Kind of like, honestly, I was thinking like a lot of ZK use cases, like imagine proving that your supply chain meets requirements without revealing your suppliers, like that type of thing. Like you do a ZK circuit, it's like, no, it's like easy, like rip through shipping this. For products like exchanges, like Hyperliquid's sick, but did they need to build the blockchain, right? And maybe they did need to build a blockchain for the reg arb, but like you can now make your exchange fully verifiable. You can make it private, and you can also have compliance checks in there. And your customers can verify that it's private and that those compliance checks, they can read all the code. So now you can have things like dark pools, but they're compliant, or transfers or trading with minimum traceability and compliance checks. And this is like, see a lot of customers kind of going in this direction. Another one that's kind of more niche, but just like happens to be some really, really, really big customers coming to us asking for, is basically kind of using off-chain data in their systems, kind of more like PII type stuff, to authorize actions on chain. So like one really interesting example that I've seen from some very major institutions is kind of, they will stamp like they're running this, but they need it to be verifiable on chain. So they're basically doing stuff like authorizing under-collateralized loans. Maybe you need a giant under-collateralized loan for the weekend without revealing any details. So this would be kind of, you need to build a ledger of like how much of like their outstanding debt you've authorized. And this makes building an app like that go from like a headache to a single prompt, right? Yeah, and then you could ship stuff like entirely verifiable VPN providers, anonymous overlay networks. Like every single part of the stack can now live in the enclaves because you have given them state. For AI specifically, kind of assuming you can have the resources to do the inference at a cost that makes sense, as Marvin hit on. You can do training over sensitive data sets and never expose any data outside the enclaves. Private inference sessions, fully verifiable clause that operate on completely private state. Yeah, there's other stuff, but yeah, we had to stop somewhere. Yeah, so kind of hitting back on it again, like if you're a developer and you've built in the Web3 space for a while and you're just trying to do something simple in the Web3 space and it's so hard, like This is simple to build with, fast to iterate on, performant, and scalable. So kind of I've been going around everywhere, so I wanted to make a little diagram of how this all fits together. So at the bottom, we have T's, we have the reproducible builds, we have the operating system. On top of the operating system, we have all the infrastructure and tooling around boot proofs and app proofs. We have the verified persistent state. And in the example, like, I'm saying Postgres, you could put any other database in here, but we're going to do managed Postgres. And then you have your apps on top of all of that. Yeah, that is pretty much it. So yeah, we're currently in private beta. We have waitlist of customers. We are very slowly kind of onboarding higher priority customers, and yeah, it's rolling out. It's being built. It's in use. But yeah, any questions?